Hi everybody, welcome to the stream. Let's see that amazing internet. Yeah, no, hopefully this works out. So how's the audio? Everything good? Is it laggy? Nice background. That's good. All right, so let me go ahead and bring up this. So where's the tier tree stuff? I don't even know what that is. So this is going to be week 10, day 1, and the stream is happening now live. And yet again, YouTube failed. So I think we're going to give up on YouTube and then do Twitch, and then I'm going to experiment with WebEx as well. My fear with WebEx is the resolution of the image. So we'll see how that goes. Anyways, the attempted next class is going to be at 12 p.m. this Thursday. So in 48 hours from now. And you know, we'll see how it goes with the internet. If you kept up on Discord, Cox was outside and they've been doing some things to my internet. So hopefully they don't decide to do it right at lecture time. In fact, it almost happened now. So anyways, but FPS is like 2. Yeah, see, that's the thing with WebEx. It's really like, so it's, but I mean, it's because it's really working, getting everything live. So anyways, let's talk about first something that I posted on Canvas. And so I went ahead and posted on Canvas a little quiz called Midterm Exam Tech. And that is going to be sort of a test run of your midterm exam 2, which until we figure it out exactly, you can expect it to be not this week that's upcoming, but the week after that. So 2 weeks from maybe today, but we'll figure that out. What I want you guys to do is we need to figure out a time that everybody can do it. And most likely it'll be in the afternoon. However, if we can't figure this out, then I can also make it so that you have it during your regular class time. So we're discussing hash tables once we get to that. But right now we're talking about the midterm exam tech test, which you can see, but it's not available. It'll be available tonight at 6 p.m. From 6 p.m. to 11 p.m. And it's available for 30-minute time. So you can take it anytime between then. But the way I want to do the test is I want to make it so that it's available in maybe like a 4-hour gap of time and you have 3 hours to do it. And I will make the TAs take it first and then add to that ×2 the time that they take to do it. And that'll be the time that you have to do it. So that should be plenty of time since we're not limited by the classroom. Could you set it to be able the whole day, but only 3 hours to complete the exam? So I don't think the whole day, but I'm thinking maybe like a longer period of time. So what we need to do is we need to coordinate this. So I'm gonna put in a poll with Google and also on Discord, and then we'll figure that out. I'd rather have that be more of a 6-hour period or something like that, or maximum of that. And if we just can't coordinate, then the backup is you will have it during your class time. So that means you will have 8:30 a.m. for the 8:30 a.m. people, 10:30 a.m. for the 10:30 a.m. people, and then 5 p.m. for the 5:30 p.m. people. So, because, yes, even if I do add that 6-hour range, I'm scared that there will be people that don't have the availability during that. So, anyways, the quiz is going, when you start the quiz, it will ask you for an access code. That is going to be test code. And I also posted it on Discord. And then I think that is so that I can like give it only to certain people. So which is what I would do if we end up doing different times. Otherwise it'll be the same code for everybody. And then it's a 3-question test. The questions are supposed to be in random order. There's no web locking and there's no webcam required. Well, yes, you only have 3 hours, which is enough to figure out whether or not, I mean, you should know ahead of time you have the time available. And if you don't, you have 3 hours to figure out what you can do if something happens, like your internet dies or things like that, or to contact me. So that's why you want to do it in the beginning of the 3 hour, or if a 6-hour range, you want to do it the first 3 hours. But if something happens where you can't start it, then you can figure that out. So it's a buffer. It's not meant so you can start it in the last 3 hours, because then there's no point. So yes, like I said, we'll figure that out. But this is kind of like the test run of actually how we do it. So the 3 questions here, one of them is just a multiple choice question. Easy way to test if that works. We've had that before with other quizzes, like with the syllabus quiz. Then there's an essay question. That means it's literally like the questions you get on the test, where you have a question and then there's a spot to write. The only limitation here is you can't draw because it's text. So That could work for some questions that require, yes, we're testing the test, that's right. That will work for questions that require like writing, but not for questions that require like drawing. And this is actually a very draw heavy test. Like the first test, I guess the sorting kind of useful, but really this test is like drawing. Like you guys are going to be like Bob Rosses when you're doing the test, because you're going to be doing all these happy trees and so on. And so because of that, that's going to be the third type of question, which is called a file upload question. And this file upload question is going to it's going to require you to do a tree. And I think I make you draw a tree from a traversal or something. I can't remember right now. And so for that one, you can draw however you want, even if it's a piece of paper, even if it's on paint, even if you have a tablet, whatever. Yeah, you can use your Osu tablet for this. I don't know what that means actually, but I'm assuming it's some anime thing. So yeah, so you draw it in whatever you want, and I can give you a web page that I found where you can draw things online as well. And then you take a picture of that, and then you upload it to the question itself. And yes, I am going to have to figure this out built into the time. I think the worst case scenario is people who have to do it by hand, take a picture with their phone, email it to themselves to the computer, or transfer it via USB to the computer, and then upload it to the question. And here's the part. The questions are going to come one at a time, and when you finish a question, you can't come back to it. And so because of that, you need to be ready for these questions to be anywhere in the test. That may change. Maybe I'll make it so the questions are fixed, or at least so the questions that require uploads are fixed. I'll figure that out. But yeah, that's why this is going to be the proof of concept. And it's extra credit, so do it, because if you get it right, you get extra credit. But if you don't, you should still do it, because this is the way that we're going to test. Whether it's more of a test for you guys than a test for me. It's a test for you to make sure that you can upload files with drawings of trees and be able to take a quiz and make sure it works in your browser, I suppose, and that sort of thing. So yeah, any questions on that? That's happening tonight from 6 to 11 p.m. Those are the typical hours that we seem to be on. Wouldn't it be bad if we can't go back to the old question in the real exam? Well, so here's the thing. I'm scared that if the questions are in the same order, then you're all going to have a group chat and do them at the same time together. So this makes it a little bit trickier to do that. Of course, somebody can still be the victim, take the test first, take an L for the team, and then distribute the questions to other people. But of course, I can't limit you from doing that. But at least this will sort of try to deter that. And yes, this test. So this, what's a better word than test? This experiment that you're doing is to test whether the midterm will work correctly. And it's a 3-question long mini midterm, which is for extra credit, if that makes sense. Okay? I don't know how much of the delay. Anyway, how many people do we have online? Let's see. We got 45 viewers. That's good. Okay. So with that said, we will come back to that at the end of the lecture maybe. But now I guess let's just start talking about hashing. And so some of you guys sent me some DMs saying that you wanted me to move around more when I'm giving the lecture, and you wanted me to do some like board work. And so I went on Amazon and bought this sort of like head camera that I can put on my head and then use one of the boards that I have here. So you know, I think I should just give that a try. So how about I do that? So let me put the camera on. All right, guys, there we go. So now I got that camera mounted in my head. Would you look at that? Such a nice view, huh? Yeah, got pretty lucky finding this apartment, you know. It's a nice place to spend some time reading, you know. If you're curious what I'm reading, it's pretty nice, but it's not the best, so whatever. Anyways, so let's go ahead and do a little board that people wanted. You know, we gotta give the people what they want. So yeah, there we go. This will do. So grab ourselves a little marker. And so let me introduce hashing by first talking about why it's useful. So suppose that we have a bunch of phone numbers connected to a phone book, and what we're trying to do is we're trying to store data for each phone number, like the business name and what they do and things like that. And so, we want to be able to make it searchable based on the phone number. And some of the possible data structures that we've talked about to do that are things like an array, a linked list, a binary tree, or maybe even a heap. So how could we do that? Well, if we have 10 phone numbers, we can just dump all of them into an array of size 10, make the array something like this. So suppose we have a little array. We got maybe 10 phone numbers in there, or maybe less than 10. Here we go, 1, 2, 3, 4, 5. And each of these are like objects, and each one has an object of like phone book entry. And then in one of those spots, we can have the phone number in there, and then in another one, we can have the company name and so on, right? And so, if we have 5 listings, then we just need an array of size 5. Similarly, if we're working with a linked list, each of these can be linked together to store all 5 of them, right? So, 2 more of these. It could be singly or double linked list, doesn't matter. Another way of doing it would be using a binary tree. So, we could have even an ABL tree or just a regular binary tree, and maybe it is something like this. And the way that we're inserting into the binary tree could be based on the phone number, right? We could even be using a heap, although that'd be kind of weird because we don't really get an advantage in storing things that way. So here's the thing. If we do this with an array, and we're trying to do the main 3 things that we're trying to do with our data are going to be information retrieval, and that can be kind of summarized into searching our data, potentially deleting information that we no longer need, such as if a business no longer sells, or if we're trying to add a new business. So if our data is unsorted and we are working with something like this, well, if we're trying to search for something, it's going to take O(n) time, right? So let's go ahead and write that down. Let's pick a green marker for that. So this can take potentially O(n) time. Hold on a second. I don't want to. There we go. Okay. What about the linked list? Well, again, if it's unsorted, we could do it in O(n) time. And the binary tree, technically O(n) time if it's a degenerate tree, right? So that brings us to a good point. We could actually make this n log n, or sorry, just log n time. What do we need to do for that? Well, it has to be some sort of balanced tree, so such as an ABL tree. Similarly, though, we could sort these based on the phone book and sort, so for example, if one of the phone numbers is 702-895-400, then this one's going to go before this one in this list, right? So we could sort it, and then we can find entries in our phone book in better time than n time. We could actually do it in log n time. What about the linked list, though? Can we do that in log n time? By the way, how can we do that in log n time with the array version? What algorithm do we need for that? Yeah, that's right. We need a binary search for that. So if we have binary search, we can achieve searching for information in a sorted array in log n time. Can we do that with the linked list? No, we cannot, because we cannot implement binary search on this, because with binary search, we can very quickly move around the array here by just, dividing by half and so on between the pieces. We can't do that here. We have to actually dereference the pointers to do that. So there's no easy way of achieving log n time with a linked list. But that's okay, because we have our binary trees, which is essentially like, a hyped up linked list. And if it's a balanced tree, then as you can see here, the height is going to be log n, which means that we can search for anything in login time. Okay, so that takes care about searching. But what about deleting though? Deleting with an array is not so easy. It messes things up. With a linked list, piece of cake, it takes constant time. But with this, if we're trying to keep it tight or if we're trying to keep it organized, if we delete something in the middle here, what are we going to do with these two? Are we going to shift them back? Are we going to leave them there? It's going to keep growing. It's going to waste space. And with a heap, it's just not really going to work for this problem at all. So let's just kind of get rid of that one. There we go. Or here, you just erase it. So all of these, the best that we can do so far is login time. So can we do better than that? Can we have information retrieval faster than login time? And the answer is yes, we can. We can do something called direct access table. And what that means is, suppose that we went ahead and said, okay, we got 5 phone numbers here, and what we really want to do is, if we can make the phone number itself be the index of an array, then all we have to do to find it is just put the phone number in. So let me simplify that for a second. Suppose that, you know, we're back in the beginning of the 20th century and we have phone numbers that are like 3 digits long. So we got phone number 333, maybe 456, and 123. Okay? And suppose that all phone numbers are just 3 digits long. Well, couldn't we just make an array of size 1000, going from 0 to 9999? You know, make an array of 1000 size, and then in spot 333, which is technically the, if you start counting from 0, 334th spot, and spot somewhere here like 1, 2, 3, and then spot 4, 5, 6, which maybe somewhere here, and then of course this is like the beginning will be spot 0, and the last one will be spot 999 all the way here. If we kept an array of that size, then we can just store all these 3 phone inbox entries into the spot where they would go into the array. And then if I want to access any of them, you know, suppose that our array is called A, we can go ahead and do something like A, what is it, 333? Yeah, A333, and bam, we are at the spot that we want to be at. And that's constant time of 1. That's much better than login time, right? In fact, that can be achieved for any of them. Now, what if we were to search for phone book 111? Well, it's not found. So what can we do? Well, let's make this an array of pointers that they point to the object if the object exists, which would be the case for these 3, and the other ones just set them to null. So if when you go ahead and check that, you know, you see that it's equal to null. So you're like, if a.x, x being the phone number you're looking at, is equal to null, or actually maybe not equal to null. If it's not equal to null, then we can go ahead and do whatever we want to do. Otherwise, then you can go ahead and print out to the user, you know, like not found or whatever. And so on. Suppose we have namespace std. And so, you know, we don't need any of those really hard implementation of data structures. We just make a big array. You know, if as long as it's an integer, we can basically make an array of the size of the biggest integer, and bam, we're good to go, right? We can slap and call it a day and move on with our lives. You know, go watch some TV. I don't know. Well, what's the catch here? The catch is that you need an array of size 1000 for 3 numbers, and you're gonna have basically less than 1% usage here. It's 6.03% usage, I believe. Basically 3 over 1,000% of usage in the array, and everything else is wasted. And if we expand that to now going with a real phone number, which has 3, 6, 9, 10 digits, we're gonna need an array of size what? Well, let's get some space here. There we go. So we need 1 0, 2 zeros, 3 zeros, 4, 5, 6, 7, 8, 9. So one more 0, I think. Yes. So then just make this all into like that. Yeah. So we need what is that? 10 billion. 10 billion. An array of 10 billion integers. Multiply this times whatever the size of an integer is in your computer. So suppose that's 4 bytes. Then this is going to become, this would be mega, giga. So this would be, I might get this messed up. I don't know the math. So this would be kilobytes, megabytes, gigabytes. So yeah, okay, 40 gigabytes. However, you're not just storing an integer in there. Maybe you're storing the phone book itself. And suppose the phone book takes, I don't know, another 8 or 12, let's say 12 bytes. So that means multiply this times 3. So about 120 gigabyte array. I don't know, you could probably make that with a vector, not with an array, and you'd be okay. But it's still quite considerable amount of space. And not the, sorry, I'm a little tipsy, I guess. Not quite ideal. However, you know, we come back to the thing we talked about quite a while ago, the comparison between space and time. If you really care about space, being able to access that phone book really fast, so suppose you're calling in, what is it, like 411? Whoever uses a phone anymore these days. You know, you're calling to get a phone listing. You know, they can get back to you in one time versus login time. And if you got tons and tons of phone records there, that login time is going to be slow. And you're going to be impatient if you're waiting for somebody to tell you the phone number or if you're Googling something, right? So this is much faster than login time. Constant time is always going to be best at the cost of a lot of space. So can we find some balance between speed and space? And that is where hashing is going to come into play. So hashing is going to take the idea of mapping your data into this array using not something so literal as the phone number, but converting basically a value into a particular key using what is known as a hash function. Hash function. So what we want to do again is we want to take data that, by the way, obviously here it's very nice, and a phone number is an integer, but what if it's not an integer? What if it's words? Well, we can quantify it in some way and make it into a number, but ultimately once we have a number, we want to take that number, feed it into this magical hash function that is going to take that value and map it into an array that is not necessarily the size of 40 billion entries. But if we know for a fact that all we got are 3 phone numbers, you know, we got the 323, 456, and then whatever the other one was, 323, I don't know. If we only have 3 digits, then ideally what we want to be able to do is this. If we know for a fact that we only have 3 phone numbers that we got to work with. What happened to my red marker? Here we go. I like the red better. So if all we know is we have 323, 456, or what? I don't know. Maybe that's a 9. Let's just make it a 9 now. And then maybe we have 555. And let's say we got one more, so like 111. Okay? if all we got is this number, this number, this number, and this number, we don't need an array of size 1000. We just need an array of size 4. We just have to find a way so that these 4 values are fed into something which is going to be our hash function, which we can call h of x. And that's going to give us, hopefully, indices that point to this array. So we take our data, which are our x's, and we feed it into this h of x function. So for example, if we feed h of 3, 3, 3, we want to get back something unique that is different than something like if we feed h of, 5, 5, 5. We want to get different things here. So for example, what could we do actually? How about you guys tell me? What do you think? Let's check the chat. What do you think? What could we do here? Well, if we look at the phone number, we can see that the last column of digits here are unique, right? So if we just take that last column of digits, H333, we can make our hash function return to us a 3 on that. We could make this one return to us 5, this one 6, and then this one 1, right? And then now we can store this, not necessarily in the tightest possible space, but definitely not size of 1000. Here's an array now, 0 to 6, size 7. And so now, here we can store 111. Then we can store 333 here. Then 956 could go here. 956. And then what's the last number? 956, we did that one. What am I missing? I got 4 numbers there and 3 things. So we get the 111, we got 333, 555. Oh, my bad. It's very loud. My neighbors, I don't know what they're doing. You know, I gotta go check on them. What's that pigeon doing there? Yo, pigeon, you're distracting me. Get out of here. Yeah, stay out, pigeon. Sorry. Damn pigeons, you know. Trying to look for food or toilet paper, but I'm not gonna get neither. So anyways, so I was saying, here we have our 4 phone numbers, and we're feeding it into this magical hash function that is going to return to us unique indices. Now, it's not so magical because all we are trying to do is extract that first column. And so now we can store all 4 phone numbers in an array of size 7 and have that O of 1 time. Now, what is this magical function that can extract that last digit? Well, we can use modulus for that. So really our hash function is going to take x mod 7, because now if we take 111 mod 7, that's just going to give us actually that'll work better. So okay, so now if we take that mod 10, that'll give us 1. 333 mod 10, that'll give us 3. 956 mod 10 will give us 6. And 555 mod 10 is going to give us 5. So this awesome function is going to be our hash function. So really, when we're coding h of x, it's just going to take x, take mod 10, and then return that. That says return. So yeah, that's basically what a hash function is going to do. Is going to take our current values and map them to a particular key here, particular index, using our hash function. Now this is an easy example because, you know, we got a few numbers and we can see that they're unique. But let me introduce you to the little concept here. Suppose that we had another phone number using the same system we've set up, you know, some other guy bought a brand new phone number and he got the number 221. And we try to apply it. And we feed it into our hash function. So we're gonna have to do h of 221. So 221 mod 10 is gonna be 1. But look, we already got something there. What do? Do we overwrite it? You know, because as we had it before, if we're trying to access data or even delete it, if we're saying, do we have phone number 223? We feed it into our hash function. In constant time, it tells us 3, and there's, boom, we have something. If somebody asks us, do we have phone number 454? We feed it in, it gives us 4. We see there's nothing here, there's a null. So we say, no, that's not existing. But in this case, if we get 111, we see that we have 111. But now we're feeding it 221, and it's also putting it there. So what are we gonna do? Are we gonna like overwrite it? We have what is known as a hash collision. And this is going to be the problem with hashing and sort of the catch. So with the direct access map, it's impossible to get a collision because every single value will map to a unique spot in the array. But here, because we are taking bigger data and sort of squishing it into a smaller spot, but still trusting that things will map uniquely, the fact of the matter is we can't always guarantee that's going to be the case. Because there are going to be things that collide. If we have more combinations here than we have spots here, then there will be a collision where two combinations will map to the same spot. It's impossible if we have 1,000 numbers here, and even if we have here like 998 spots, but 1,000 numbers that have to map to this array, then I guarantee you 2 spots at least are going to collide. Because unless we had 1,000 here and 1,000 numbers here, then we could say, if we do it as a direct access table, that there will not be any collisions. But because this is smaller, or sorry, this is bigger than the array, then there will be a collision somewhere. And there might be more if we do it badly. Hopefully, what we're trying to do is make the best function for the least amount of collisions. But that's very hard to do. In this case, what will be the solution? Well, there are many ways to solve collisions. I think I'm gonna go back to the iPad now because I'm kind of tired of moving around, and we'll talk about them. But basically, one of the things that you can do is you could put it on the next spot available. You could create a chain of them here so that you could keep both of them together. So you could keep like 221 here. But all of these collision resolutions are going to cause a problem with the access time, because the access time is no longer going to be O of 1. However, in the worst case, it's just going to be O of n. So ultimately, even if you screw up your hash function really badly, you're still going to have a O of n in the worst case. So I hope this is a nice little introduction to hashes. Now, before I go down there, I'm just gonna grab some water, and then I'll come back to talk to on the iPad for the lecture. So here we go. Just gotta get some water from my bucket here. What the hell? That's right, baby. Whoa, whoa, come on, man. What the hell? It's we had problems with the stream last time, so I told them to come fix the internet, so I guess they're fixing the internet, but now they messed up the roof. Jeez, and oh my gosh. Well, anyways, now that I got my water, I'm gonna head back to the iPad. I got nice little paintings and everything. So all right, let me just get some water out of there. Actually, you know what? I'll just take a soda with me. So, all right, then let me go ahead and put the camera back. Can anyone hear me? Welcome back to the video. He's lagging. Oh no, you guys couldn't hear me? Oof. Say something in the chat if you can hear me. You couldn't hear us. That was entertaining. We could hear you, but you couldn't hear us. We can hear you now. Say something. I think there's a big delay happening now. But anyways. So there you go. Happy April Fools, everybody. So let's go ahead and recap what I talked about in case you missed some of the stuff. So, my eyes feel weird. Okay, so the summary of this is that when we're storing data in an array, even if it's sorted using binary search, it's log n time. And by the way, I couldn't see the chat. I was acting that I could see the chat, but you know, I didn't want to fiddle around with it and have it break in the middle of the lecture. So, GG's. So, anyways, like I said, happy April Fools. All right, so to summarize that could be actually summarized rather quickly. So I think that was pretty dope, yes. So even if you store data in an array, even with sorted array, log n time with binary search is the fastest you could do to accessing the array. And then if you try to delete something, it's gonna mess things up because you gotta shift everything around. So not ideal per se. Furthermore, you got access, retrieval, and searching, right? So any of those, log n time, and even deleting causes more problems. With a linked list, you can't even search in log n time. With a binary tree, you can do log n time. You can do everything in log n time, search, delete, find, but it's still log n time. To be honest, if you wanted a quiet room. Yeah, so I was actually thinking if we do this for real, like a full lecture, I could set up the chat on one side and then use Google's, I forget what it's called. It's a VR drawing app where you can draw and it's smoother. But the problem is I have to make sure I move my head slowly, otherwise you get motion sickness. So I don't get it because I'm experiencing it, but you get it because you're not experiencing it. It's like watching VR versus being in it. So anyways, so ultimately, what if we make an array of our phone numbers and the array size is the same as the size of the biggest phone number? Then the phone number itself can be an index to find the value in constant time, because that's just O of 1. It's in memory contiguously. So if it's the fifth thing, then you got to go 5 spots down. If it's integers and it's 5 integers down, that's 5 times 4, 20 bytes, right? And so that's what's known as a direct access table. VR Classroom 1. I'm down for that. That'd be actually pretty cool, but I don't think we all have VR. So anyways, that will be a direct access table, and you can achieve everything O of 1. But what's the cost there? The cost is, if with phone numbers, odds are that not all phone numbers are used at one time. Otherwise, we'd run out of phone numbers. So there's going to be a lot of wasted space where a phone number doesn't exist. It's not assigned to anybody. And so now you still have to allocate that space because the array of the size of the biggest number, but it's not being used. So it's inefficient in space so you have the balance. O of 9999. Well, why would it be 999? It'd still be constant time, O of 1. Space-wise, it would be O of, I suppose, 999, but that's not 99. It would be O of n for space. However, in this case, actually, no. It wouldn't be O of n, because if we have 10 items and we make an array of O of n size, that's size 10. But if these items are phone numbers, we still need an array of the size of the biggest potential phone number. O of the custom VR equipment. Oh, well, it's far more than that, actually, if you think about the PC cost as well. And by the way, I have a 1080 Ti, so if it was stuttering, that's the internet's fault. That is not my fault. It is super smooth in game and super HD. You will see when I upload the video, unless the recording software also screwed that up, that it is in high definition. My rig is not a joke. So, okay. So basically, what if we want to take the idea of this direct access O of 1 time, but apply it with something that is a smaller size array? And that's where we're going to have our hash function that I was talking about. So we have a value x, which is our phone number. We're going to feed it to this math formula, which is this hash function, and it's going to return to us an index in an array. And what we do to do that can be whatever you want. And then in the case of the video, in the stream, I was doing modulus. That's a very convenient hash function. But as someone was asking, and as you saw, what happens if two people have the same last digit? And then that's when you enter a collision. So a collision is, ideally you want this value to be mapped to a unique spot. You don't want two x values to map to the same index. Ideally. However, it's very, very hard to achieve that. Why is it very, very hard to achieve that? Because first of all, you need to know what data is coming in. Second of all, suppose that you have 10 items that you're inserting and you have an array of size 100. In that case, at most 10% of the array is going to be full. Okay, so even if you just pick randomly. So suppose your hash function was random. Now that's bad because then you can't access the data, but you're just storing the data. If you make it random, then odds are that, I suppose you, if you with the math, but I think you have 10% chance of picking a spot that you already picked. Although I don't think it's that easy. I think it's that combination permutation stuff that we were talking about the other day. So ultimately, even a random function, you'd be okay. But suppose you try to do the same thing where you have 10 values that you're trying to store in an array of size 11. Very, very likely, in fact, something like 90% or higher, maybe 91% or something, or chance that that you will have two of them crash into the same spot, collide. And so that's going to be the trickiness of the hash function. And also, because, I mean, it should be obvious that if we have 100 values that we're trying to store in an array of size 10, then things are going to crash into the same spot because you can't even store enough data there. So that should be relatively obvious. So we at least need to have it of size 100 and then hope for the best that they map. This is the dream right here. We have 100 values, we feed it to some hash function, and they store it in 100 spots. No collisions. That's perfect because then we're achieving O of 1 time, and it's not costing us extra space. However, very, very, very hard to achieve because you need to have a special hash function that's going to be able to map things uniquely this way. And you might think, oh, well, I just named them 1 through 100. Yeah, no. But here, the data that you're storing, so those are going to be the values that you're mapping, and they generate your keys, which are the indices. These values, they may not be integers. They could be words. They could be any kind of data. And the process of you quantifying that data is the first step. And once you quantify it into some sort of number, then you're feeding it to the function to get an index. That's another step. So either of those steps, how do you quantify letters? Well, that's easy. Letters are easy because you just pick the letter of the alphabet, right? A through Z. But then suppose that you have words. Well, are you going to pick the last letter and make that be the case? Well, what if two people have the same first letter? So now maybe you have to take, say, Tom, Jerry, and Tim, and Anna. So suppose that you're storing these 4 values and you're trying to store them in a hash table because you want to have that O of 1 access time. Well, you could try using the first letter, and then, so we have T, J, T, A. The problem there is because we're feeding this with some math formula, if you feed it a specific number, you want it to give you the same value, so you're going to give you another value out, but that value should be the same. So if I have a math formula that I feed it 5 to, and this gives me 10, then I want it that every single time I give it 5, it's going to give me 10. I don't want it to randomly give me 11, and I don't want it to randomly have something that I give it like a, well, if it's a collision, it would be if I have it something that I give it a 2, and it also gives me 10. But what I do want is to be consistent. So here's the thing. If I have two T's, then that doesn't work, right? Because we got the two T's in there, and they're both going to give me the same value. So I could try the last letter. Well, what's the last? I haven't even talked about how to convert that into an integer. I'm just simply talking about input. Well, on the last letter, I have M, Y, M, and A. That doesn't work either. So what can I do? Well, I could try a combination of the first two letters. That'll probably work because I got T-O, J-E, T-I, and A-N. Now, those are unique. That's perfect. If they're unique, then I'm already one step ahead of the game because now I have to feed it to a hash function that converts that into an index. So suppose that I'm storing this. I'm trying to be super efficient here and storing it into an array of size 4. So that means 0, 1, 2, and 3. Now, what I need to create is I need to make a function that's going to take those values, and I don't really care what order they come out in. I don't care if TO gives me a 0 and JE gives me a 1. But what I do care about is that they all give me a unique value from 0 to 3. I don't know why I put that in there. So TO, JE, or GE, I keep saying JE, TI, and AN. I want all these 4 values to give me unique numbers that represent those. So one of the things that I could do is I can convert them into the ASCII values. But for that, I need an ASCII table. So that's too much effort. So let's just go ahead and use the alphabet order. So A is a 0. And then what is... Okay, chat, you got to help me. What is T and what is S in the alphabet based on this? Which letter are they? Oh, man, I hope there's not that big of a delay. Come on. You're going to make me Google it? Are you guys still alive? Everybody's so quiet. T20. Okay, perfect. I believe you. If T is 20, then S is 19. Yes. Okay, perfect. Okay. What about the O, E, I, N? What about those? What is O, what is E, what is I, and what is N? So let's write these down. A is 0. S is 19. T is 20. J is 10. No, J is 9. Which one is it? And then O is 15. N is 14. Did I get them all? E. E is 5. And then you guys say J is 10. Oh, A is 0. Oh, is it all screwed up because of that? It's okay, guys. It's okay. Let's just say that in our world, those are the letters that represent in the alphabet. Just subtract 1. Too late. It's staying like that. But anyways, let's just say that this is the actual order in the alphabet that those letters are at. Okay? So what if we make our little math formula? So J is 9. Okay, we'll just make J 9 then. But I don't know. It doesn't really matter. Alternate universe, where we have the dystopian Half-Life universe. So it's all good. So, okay. So from there, let's just go ahead and add the numbers together. And in other words, add the letters together. So we got TO, which is going to be 20 plus 15, which is 35. We got JE, which is 9 plus 5, which is 14. We got TI, like my 1080 Ti, that is 20 plus, did we not do I? Did you guys do I? I is 9. Okay, thanks. Wait, J is 9. You got so what is J then? If J is E, so it must be 8, I guess. Right? Okay. I would be 8. Okay, I hope so. And then AN, which is 0 plus 14. If somebody just jumps in right now and then they don't know that we're doing this weird alphabet version, they're going to be confused. So, okay, this is good. Now we are talking in numbers here. We got little numbers here, and they're all unique numbers. So now, what we got to do is we got to take these numbers and map them into 0, 1, 2, and 3. How can we do that? Well, we could do some math. No, they aren't. There's a mod for Half-Life where you can see Twitch chat on your palm. Oh, I'll check that out. JE and AN collide. Yeah, good point. JE and AN collide. So this isn't really gonna work because even though they came from different input, JE and AN, mathematically, they give us the same values. And so, again, this would be a collision that you may not expect. In fact, I actually wasn't expecting it. I was going to give you a fifth word that would have given you a collision. But, yeah, we didn't expect it. So, very good suggestion. Let's try doing multiplication instead. Okay, so then let's just go ahead and do multiplication. So in that case, oh man, that's a big numbers for the class, guy. So that's 0 for AN. That's 160 for TI. JE is 9 times 5, 45. And then the big one, which I was saving for last, it's 300, right? Okay, this is good. These are unique. We're good. Heck yes. Okay. So now, we just gotta map these values to the specific 0, 1, 2, and 3. Easy solution, we could just hardcode that and say 300 always gives us this index. We could do that, but that's kind of ghetto. The other thing that we can do is, you know, it's almost good if we just take the first digit in all of them. We could take this digit here, this digit here, this digit here, and this digit here, and it's almost good. We just got the 2 that's missing. So we could hardcode something like if we see a 0, convert it to a 2. And yes, that was going to be the next point. This is working fine as it is now, but suppose that somebody's name was Nanny. Nanny is going to collide with Anna. Right? And so, yes, multiplication won't really work. So you can already start to see that it's not so easy to make this magical hash function that maps things to an index where they're unique. That's right. It's Nanny. So Nanny breaks our hash function, you know. So we can try multiple things. However, let's just stick with this one for now. How do we go to the final step from here? Well, I'm trying to do some math. See if I see a pattern here. That could be a 9, could be a 7. Nah, I don't know. But anyways, we can just hard code it so that everything gets subtracted minus 1. And if it's less than 1, it doesn't. So then like we could say that take 4 and subtract 1 from it. Take 3, subtract 1 from it. And if value is less than 2, don't subtract. You know, and that way 1 and 0 stay the same. And bam, we mapped it. But as we saw, we already have a problem. So ultimately, this is a very tricky situation. As you can see, we could do other things. We could try to do modulus on this, like 4 mod 5 and so on. And so the point is, I'm not trying to find a solution to this. I'm trying to make the point that it's a hard problem to figure out. With the phone number example, it was very convenient because they're numbers and there were no collisions, right? However, how could I guarantee that there's no collisions? Well, I could literally take every single letter there and make it part of the index. So I could just convert every single letter to the value here and then make them indices. But what is that going to cost? That's going to cause the array to be really, really big, right? So if I simply say this number and then if it's the second number, then we add times, we multiply times 10 and then add the next number. And so we're just converting each letter into an index. There may still be collisions, but more than likely there won't be, and it's going to be really, really, really big. So to summarize, our hash function allows us to take input and convert it into some index that we want to store. And it can be anything. It's a function in C++, so you can code whatever you want to make it work. But the thing is, you're not always going to have the entire data set. There may be more data added later on. And will your function hold up to it? As we were seeing here, you guys predicted pretty well. If we do it this way, it's holding up. But if we add nanny, it doesn't hold up. So how can we prepare ourselves for like when we add more data to it? Could we use something like the equation for finding the index of a 2D array represented as a 1D array? That's just multiplying values, not really helping us much, because the way that equation works is in C, when you're storing an array like a big block, if this is the second row, all you gotta do is multiply times the size of the row. So, I mean, it's still gonna have potentially collisions. But let me put it to you this way. The bigger we make the array, the more flexibility we have with our hash function, because ultimately here, we're just trying to simplify this to 4 numbers. And no matter how complicated we make the hash function, when you simplify it to 4 numbers, odds are that 2 things will give us the same problem, the same values. So even just making this step unique, where the numbers we feed to the hash function are unique, it mapping to something smaller is going to cause problems. So if suppose that we did our magical formulas and we converted the text into the following numbers. When we feed this to our hash function, it may still give us a collision. It may still, both of those give us 0. Such as we said, if we take that column and then we add a 5th thing here that was 32, then that's not going to be a good hash function. We could hash both all these values together, but suppose then we added something, we could do like modulus 100, so x mod 100, so it could take into consideration both numbers. But then what if we have 132? That's going to collide with this one, and so on. XY index, x times max value of y. That's what I was thinking. XY index, x times max value of y plus y. I mean, that could work. I don't know. I don't really want to think about it right now. But it could work. But ultimately, as long as you get unique values here, you're good. But you still got to figure out how those unique values are going to map to 0, 1, 2, and 3. So one step is just getting the unique values here. But the other step is actually converting those values, such as these random numbers, into actual indices in the array. So making these unique is not enough. They have to be unique, but also they have to be able to give you different values each. If 18 and 22 with the hash function give you the same location of the index, you have a collision. So if we have collisions, which we will have unless we're really, really good, how do we deal with them? So that's the next thing. But before I do that, how are we feeling on the concept of hash functions? And by the way, this array here, that is where you put things that you pass to your hash function, that is a hash table. How do we feel so far? All this mapping makes me think of discrete math. Oh no. If anything, this is one of the hashing is very easy. I think some of the other stuff that we've done is more discrete than this, especially when we get a graph. There is a function. Yes, there's math involved, but the focus of the class is not for you to try to come up with a master function that will cure everything. The focus is to understand what they are and to respect how hard it is to come up with one, so that if you ever have to do one, then you probably just download a library that does it for you. I already talked about the beginning stuff. This is all the stuff in the video was essentially what is here, minus the phone example. But I can throw in the phone example later if you want. Okay, so we're at 50 minutes so far. So I guess since the video part, I kind of, like the VR stuff, I didn't really see questions. I went kind of fast. This sounds super specific. The hashing function. Well, you can hash anything. the goal of hashing is to take data, system class Star Destroyers or ships from Live, Die, Repeat. Take those data and store them in an array, but be able to access that data, any spot in the data we can access whether it exists or not in all of one time. We're not trying to sort it, we're just being able to access it that quickly. Well, it turns out that you can convert a number very easy. So, well, okay. I don't want to jump into what makes a good hash function. We'll do that next time because I have a whole section on lectures of this. Because here's the thing. When you're using a password in a computer, you're typing a password in English or whatever. It's just an alphanumeric characters plus some special characters. What happens is that those characters are fed into a hash function that makes it into a hash that is this big, MD5 checksum, which is cracked now, but it converts those numbers into this bigger set of characters. And then that bigger set of characters is secure because you can compare that to what's stored in the server and see if they're the same. But on the user side, if I don't need to know what that set of characters is, and the server doesn't need to know what my original password is. All they know is what it was hashed to. So if I have the password let me in to log in into the Canvas and give you guys his grades, I feed that into a computer, into a login page on Canvas. You know, it goes and it generates some hash. And that means it takes these values and actually gets you this really big string, which would be like 128-bit or whatever. And each of these could be letters, numbers. Like that. And so this is what the server is storing and comparing with its local copy to see if you logged in the right password. What you do not want is if somebody else has a different password that's called cookie, like that, and they put it in, then it gives you the same hash. Because then the server is going to think that it's you that's logging in and not the other person. And so now you're logging into somebody else's account. Very, very bad. So you want to make sure they're unique. Furthermore, if I'm a hacker, you know, obviously I want to get this guy because this will just map to that and I'm good. But if I'm a hacker and I know what this key is here, can I go back and generate that from this? And if that's an easy process, then I've cracked your password. And now I can use that password on other web pages probably because you use the same password. So furthermore, can I make other passwords that make this as well? And again, that's bad because they log into your account. So, does everything hard we learn have to do with the library that does it but 10 times easier? Yes, everything that you've learned in this class and you will learn in this class is already available on the internet and a library function, and you'd never have to code it by hand. Usually, the stuff you're learning here is because it makes you a better programmer and it makes you a better computer scientist, and it just happens to be in tons of interviews. So that's why you're learning all of this stuff. Also, while you don't need to know the internal workings of a car to drive it, you do need to know how the car works in the sense that you got to press the pedal to accelerate and the brake and the steering wheel. And if it's rear wheel drive or front wheel drive so that you don't spin out if you're taking a fast turn. That's the kind of stuff you need to know to drive a car. So, however, a car mechanic that's really good may be able to push the car closer to its limits than you because they know more about it. So you can think of it this way. You're learning about hash functions, you understand them better, you know how to use them better and when to apply them. Like, you know a car is for roads and a boat is for water. You wouldn't want to try to drive to LA with a boat because it's not going to move because it needs water, right? So you need to know which mode of transportation for the required task. That's like knowing which data structure to use for the required problem. If you're trying to do a priority queue, you use a heap. If you're trying to sort data, you're not going to use bubble sort. You're going to use quick sort or merge sort. If you know that the kind of information you're trying to store needs to be accessed in the way that it's done, like recursion, and you're trying to convert something recursive into iterative code, you use a stack. So you need to learn these data structures so that you can use them, because I could tell you, oh yeah, C++ or Python, they have a map and key. And you can create a map, or also known as a dictionary, and you can store data that way. And you may not know if that's efficient, when that's efficient, or how that even works. Well, it turns out that a dictionary in C++, or I guess in Python, I guess it's called dictionary. I know dictionary in Python. I think it's the same in C++, but that's using a hash table to be able to access data quickly. But you need to know how that works so that you can use it. So you want to use a hash table if you receive a key and you need to retrieve specific values fast. You want to use a hash in general when you want to be able to access data quickly. You don't care about how it's stored internally in the computer. You just want to access it quickly, modify it, or potentially add data or delete data. So if you think about an AVL tree, you can store data and access it quickly, but you can also print it out in a sorted manner. It's very nice. You care about how the way data is stored if you're trying to do like an in-order traversal. However, if all you're doing is storing records of data, such as a phone book, you don't care about the way that they're stored as long as you can check whether a phone book is valid or not and who owns that phone number. So that's when a hash table is going to come in useful, when you do access data quickly and you don't care how it's stored internally. So how do we feel about that? So I guess for the remaining time, since I want to take advantage of every single last second, is, oh, we have a question. Can you insert or delete into a hash table? Yes, you can. And that's okay, because every time that you insert, think about the phone book example. If you have a phone and it hashes to a specific spot, if you insert that phone and that data for the phone user, it's going to store it in, say, index 55 for like specific phone numbers. So we have phone number 702-895-0007 or whatever. Let's say that that gets stored into the hash function into spot 555. So index 555. You store it there and you keep it there. Suppose that that business was a casino when they went out of business because of a virus, and now they're bankrupt. They canceled their phone number. All you got to do is put the phone number in, get to the spot, and then delete it. And then suppose that a year from now you go get a phone number and you get the same phone number, and then it's going to be stored again in index 555. So you can access or delete things very easily. Now you probably don't want the same phone number because now they're going to get collect calls, from the person that went bankrupt. But what I'm saying is it's always going to be stored in the same spot. The collision is, of course, if somebody else has like this phone number and you are using some hash function based on just those digits, and that's when you get a collision. What you don't want is that information to be stored there, because then bam, you have a collision, you're in trouble. So how do we solve collisions? Okay, so no matter how good you are going to run into collisions someday. And so how do we handle such collisions? There's two popular ways of doing that. And they are what are known, and I always get these mixed up, so I'm going to triple check before I say something wrong. Okay, so we have open addressing, which is known as separate chaining, or that doesn't sound right. No. See, I got them mixed. I knew I would get them every semester. I get them mixed up. And what I tell people is, I don't need to know for the test. You do. I already taken my test many years ago, so I'm good. So there is separate chaining, which is actually known also, and this is why I get them confused, as close addressing. And then there is open addressing. As you can see, these names are very similar. One says close, one says open. I have a hard time figuring out which is which. The separate chaining one is obvious, but which is why I remember usually that. The word chain should, if it helps you remember, you can think of linked list for that. And I guess even though it doesn't help me remember, open addressing, the keyword here being open address, meaning it can go in multiple addresses. So let's talk about separate chaining or closed addressing. Both represent the same thing. What that means is that if you're storing data, and you got your indices here for this, and let's say that you got I was trying to put my, well, actually no, I don't want to put my name. Tim and Dan, Lieutenant Dan. So suppose you're trying to hash these two names, and it turns out that they both hash. So you feed them to your hash function, and they both give you index 2, which is the third index. So the first time you could have just stored it there. But what are you going to do with Tim? Well, with separate chaining, what you do is this no longer becomes just an array. It becomes an array of pointers, and it points to a linked list. And this linked list can store all possible collisions. So here you would have Dan and Tim. Ideally now, you want it to be just one thing that is being stored there, because then you can just access it. But now, if you're accessing this, it's going to take all of 2 time. And suppose that you just have a really, really bad hash function. You want to see what a really bad hash function is? Your hash function, h of x, is literally x gets 5. Or sorry, return 5. Or let's say return 2. Why is this a really bad hash function? Because it's always going to give us the same index. It's the worst possible case that we could have. So this is going to be our big O. In that case, this linked list over here is going to be the size of the input data that we're storing in our hash table, which is going to be O of n time if we're trying to access the spot that's deepest in the list. So our access time went down from O of 1 to potentially O of n time, but at least that's it. That's if you have a really, really, really bad hash function that is always mapping to the same spot. So what can you do in this case to improve O of n time? Well, you could be hardcore, and instead of making that a, well, here, what do you guys think? Well, you got 6 minutes left, but what do you guys think we could do to decrease this O of n time? We have 43 viewers. Yeah, there's a big delay right now. Yikes. Yep, we are just waiting to see what people say. Everybody tuned me out. All right, well, I'll tell you the answer since nobody's writing anything. What was the question again? Shake my head. What can we do? Because if we have collisions, they all get stored in the same spot, and we have a linked list right now, but that's going to be O of n time. What can we do to make it so that we can access it faster than O of n time? Yes, there we go. Yes, yes. I don't want to call out the names because, we want to keep it private, but they got it right. Both of you guys got it right. Thank you, thank you, thank you, thank you, thank you. You get some toilet paper when I see it. So yes, you could put a tree in there. You could put an ABL tree, not just any tree, because this is a tree too. This is a degenerate tree or anime tree, which is acceptable in the text. But you could put an ABL tree that is balanced. And so now, if we make that into an ABL tree, suppose Dan goes in the root, and then Tim goes here, and then if we had like Anna goes there. This is now log of n. Yes, it's an anime tree. Give me some anime names and I'll put them in here. Actually, no, please don't. But yeah, so now it's just log of n time. Still not O of 1, but this is supposed to only happen if we have collisions. Normally, if we do a good job, we won't have collisions. But in the rare case that we really screw up and we have hardcore just non-stop collisions, then Utaha, that's a complicated name. It's like Utah. There we go, Utaha. rem. There we go. Enough names. So I don't know. I'm gonna Google those later probably. But anyways, so see, you just killed me. You killed my train of thought right now. Yeah. So this is only in the worst case log n if you really screw up and every single value gets mapped to the same index. That's the worst case. But hopefully, you know, it only happens once in a while, so it's still going to be less than log n time. So really, you lose nothing by using a hash table instead of just an AVL tree, but you gain a lot in terms of access time at the cost of, again, potentially space. Space is the cost here. Now, I mean, so far with all the algorithms we've done, we've kind of winged the space part because none of them have really been space intensive. With hashing, that's the first one where space can get really big. But again, sometimes, I mean, even today, I think space is cheaper than time. So you can just throw in as much space, make a massive hash table, keep things all of one time, as long as you do your hash function correctly. So that's one solution to do it. And I'll kind of go into more detail next time. This is more of a general view. But the other way that you can do it is, and this one's nasty, but it's great for test questions, and we'll really go into detail next time, is if you're hashing this, and you're hashing your Utah, and Ram, and what are the other ones where? Suppose that all three collide in the same spot. So you got Anna here, and then Utah collides in the same spot. So in this case, we're going to be using open addressing. So now this one's going to be open addressing. In this one, what you do is if you have a collision, you put it in the next available spot, meaning here. Okay? And then if rem is again a collision here, you put it in the next spot, but that's already taken, so you go to the next one there. This is called linear probing. And again, we'll talk about the different kinds of probing next time. Probing comes in from probing the array and seeing where is available. So here's the bad thing about doing this. Suppose that the next thing you put in here is nanny. And suppose nanny would have actually mapped to spot 4. But that's full. So it actually gets put here. So you can see how things start to get messy, because now suppose that I am accessing stuff. Okay, I want to find if rem is in the list. It hashes here, but because it's not there and I'm using open addressing, it may be anywhere else. So I potentially have to check the entire list n time to see if it's anywhere. Why everything? Well, okay, suppose that nanny wasn't here. Okay, I check. I'm looking for rem. Okay, it's not here. It's not here. I found it. Good. But suppose that I'm looking for Corey. I don't know. I found something there. I don't know what that is. So suppose you're looking for Corey, and suppose Corey also mapped to number 2. You check there. You check there. You check there, and then you find an empty spot, and you say naively, "Oh, I'm done. I don't have to check anymore." So, okay, you might think that's good, but let me flip it around on you. Suppose that I delete the word Utah, and again I'm looking for Corey. And this time, actually, suppose that before I delete that, I'm inserting Corey, and Corey gets put here because it crashes with Anna, crashes with Utah, crashes with Rem, and goes into Corey, okay? And goes into 5. And then I delete Rem. And now I'm looking for Corey again. I start with Anna, I go to Utah, and then I see an empty spot, and then what do? I think, oh, there must be nothing else afterwards. But there is. So because of that, you cannot just automatically assume that because you found an empty spot, that there's nothing else in the array and that you can't find it. You have to look through the entire thing. There are some ways that you can slightly tweak that, such as like marking this as at some point there was something there, but now it's no longer there, which keeps going. And if you find like a pure white spot that has never been populated, then you're done. We'll talk about that next time. We'll talk about the different probing styles next time. But at least this is a quick introduction into hashing. Hopefully hopefully you learned from this, and hopefully the VR stuff wasn't too off-putting. But if not, I kind of covered it. And I guess when I finish the lecture, I'll throw in the phone book example at the bottom if you really guys want. But that's it. We're done. So at this point, as I said, go out tonight and do the test quiz. I will be available online. In fact, I'm going to open up the floor now for questions of homework, but the lecture is officially done. So thank you for watching, and let's see if there's any questions here. So any questions? I mean, I'm going to hop into Discord voice chat as well, but if you want me to show any live questions, now's your chance. I'll wait 1 minute, and if there's no questions, then I'll end the stream. But thanks for coming, and happy April Fool's tomorrow. When will worksheets be available? Oh yeah, good point. So the worksheet is work in progress. It should be up by Thursday. It will have 3 things in it. It will have trees. Well, it'll have traversals, building a tree from traversal, ABL trees, and I was gonna put heaps in there, but I'll save that one for the next one. So that should be up by next class. Maybe tonight, maybe tomorrow night. So yes, you will have a worksheet. But this quiz will be a good practice too. When is midterm 2? As I said in the beginning, right now it's scheduled as it is for 2 weeks from now, 2 weeks from today potentially, or 2 weeks from Thursday. But we will probe on that and see when is the best time to have it. We could have it on the weekend even. I will go ahead and ask people if we can come to a consensus of a gap of time that is something like 6 hours, where somebody has a good solid 3 hours in there in that 6 hour gap period, then we will go with the official way, which is have the time at class time. So we will have the test when your normal class time would be, which is fine. It doesn't affect me. I just changed the timer on that. Other questions? So here's the timer. If it hits 1 minute, then I'll end the stream. Hope you guys like the VR part. Maybe we'll fiddle with that sometime. We still got 38 viewers. So no questions so far. Got 30 seconds left. Are hash tables used when you log into an account? Yes, they typically are. We'll talk about that kind of hashing, as I said here before. But in a way, hashing, not hash tables, hashing itself is a concept that is used in security a lot. Like encryption, security, hashing, big thing. You mentioned a practice quiz. Will it be for a grade? It's for extra credit. It will be graded, but it's extra credit, as it has been answered already. Yes, great. Other questions? Lecture will be at 12 p.m. next time. I'll check out the static stream on VR chat and let you know how it works. Yeah, check it out. Also, I will upload the video. I'll review the video. I'm assuming it's okay on the recording that I'm doing versus what it was being uploaded. So you can rewatch that, I guess, if you really had trouble watching it live because of the cutting frames. 30 seconds. Questions. Any questions on assignment 9? I mean, I guess I should reiterate, you have, in fact, I make for you an array of just data. And then that data, you have to heapify it. I have 2 headsets. I have the Oculus, I have the HTC VIVE and I have the Oculus Quest. But that was the HTC VIVE because that's the one that's hooked to my computer. I have a really big cables and I haven't set it up. I mean, I'm alone, so I have the space to do this kind of thing. Then to carry me in CSGO. I don't know if I can carry anybody in CSGO anymore. I think those days are past. It used to be LE, but now I'm probably silver. I have a ton of Smurf accounts though, so I can still play against bad players to feel better about myself. Do you heapify, or I can use it? Oh no, I can't say that because they're iffy about using certain software on these Twitch sites and things like that. But anyways, do you heapify as you insert one by one or insert all? Okay, that's a really good question because I want to point this out and people have asked it. The way you need to do this, and this is not a choice but a need. When you have the initial array, heapifying the array means taking that array, not making a new one, but modifying that array in place, you can say, and making it into a heap. That's a specific algorithm that I showed you, which is where you start from the bottom and you go up. And I mean, I'm not gonna show a full example, but I'll just show you the visuals of what that looks like. You start by, oh gosh, what have I done here? That's not what I meant to do. There we go. You start by heapifying this subtree, then this subtree, and then this subtree. But if like this guy and this guy swaps, then you gotta fix this subtree again right here. Okay? So that's heapifying. And you have to do it in place for everything. That's the first 1,000 elements. And by the way, I did have a typo that was pointed out to me on the 2 additional items. I did point it out in Discord, and it has also been updated on the assignment file as soon as that was discovered. But it's basically the last things that I entered, the J Squad and the Full Metal, that should be inserted in spots 1000 and 1001, because 1002 would be out of bounds actually. So yeah, it's just a little typo there. But anyways, you heapify the first 1000 elements, and then you insert the last 2 into the heap. And that's just an algorithm where, like, if you insert something, it would go, in this case it would go here because it's a complete tree, and then you would fix that, and potentially if things get swapped there, then you would fix that, and then potentially if things don't get swapped anymore, you're done. Otherwise you might have to fix that. So you're going back up like that. That's inserting one by one, and you will do that mini algorithm for the last 2 things you're inserting. So I want you to do both. I don't want you to just use this one for everything. I want to see you doing the heapify, because you will do this in the test. The extra credit quiz is tonight from 6 to 11 p.m. and you have 30 minutes to do it. You will need to upload a file of a drawing of a tree, and that's because that's how the test is going to run. So I want to make sure that you have you want to create a process for that. So even before you start the quiz, you should figure out how to do that. So once you do start the quiz, all you got to do is just run whatever it is you do. So I suppose I should say this one more time. Before you start the quiz, figure out how you're going to draw a tree and create a JPEG file, PDF, don't care what type of file it is. Make sure it's something acceptable that's not hard for the TS to open. I don't want some don't do like TIFF or something that I can't open easily. JPEG, PNG, PDF, whatever. Use those files, figure out a way to draw that tree and be able to have it in your computer where you're taking the test and upload it, okay? So make sure you know how to do that. And then once you got that going, then start the quiz. Yeah. If you want to use Microsoft Paint, there is an app, a website that I showed somebody else. I mean, you can use Sketch.io if that's a thing. Quick Draw with Google. Let's try that one. I haven't seen that one yet. Let's draw. Draw a clock in under 20 seconds. Okay, that's not what I meant. But anyways, that scared me. All right, I'm gonna close that. Yeah, Sketch.io. This one's good. I'm gonna post it on chat. In fact, I can pop open the this thing. Let's try that. Give me 1 second. Yeah, there we go. So look, here's a Sketchpad website, and I mean, worst case scenario. Okay, that's not the right font, but there are different things you can change. In fact, there's another one that I knew. Maybe this one. Yeah, I've tested this one before. You can even draw with friends in this one, but don't do that because that's cheating. So, you know, not saying you should do this, but that's one way to do it. You could also just go with Paint. You know, there's no shame in Paint. Because with Paint, you can even like... Why is that so big? Oh my god, that's toxic. Come on. There we go. That's still kind of big, but you know, you could do that, and then you could do 45, and then like 20, and then you can put that, and there you go. And really, this is the stuff that you would be doing. It's the tree stuff. That's really for this test, and a little bit for the hashing. I do believe hashing is the last subject that will be on the test. So when we finish talking about that on Thursday or on next Tuesday, that's when we'll finish that. So yes. All right. Ideally, though, if you have some sort of iPad or something, then you're good. I mean, you know, just draw. Oh, there's lag. Whatever. I'm drawing pictures. It should be okay. So, anyways, additional questions before the stream ends. How are your other classes doing? I hope they're doing good. We have a little timer. I would jump more into VR, but I gotta be on Discord office hours. What do we need to study for the quiz? Trees. You need to study trees. I don't know. I mean, I make you build a tree from a traversal, and then I think there's a conceptual question, which was I got the idea from the voice from the stream, so you could, you know, I guess I wouldn't recommend it, but in the middle of the test, you could try to reopen the stream for that. By the way, the test will be technically open notes because I can't stop you from Googling things. So. All right, other questions? 30 more seconds. Yes, I did. I did a dual major actually, and one of them was that. That's why I like all this media stuff. But I always intended to do graduate school with CS. So I took, even though I did that, I still took a lot of STEM classes. All right then. Well, if there are no more questions, then I'll hop onto the Discord voice chat. And, oh, I got a phone call, so I should pick this up, I suppose. All right. Well, see y'all.